All right, everybody. Lecture 8. Lecture 9 is going to be pre-recorded. I will not be here. So I have to go to a meeting with my funding agency. I do research for the American Iron and Steel Institute. So probably one of the reasons why they thought it would be a good idea that I teach this class. Something about like AISI and steel. Is there any connective tissue there? I get it, it's too cold for the laughs. Is that what it is? Yeah. Although, somebody decided to make some snarky comments on teams that I put the steel logo for the teams class. Everybody went, whoa, hold on. But when you go into AISI headquarters in DC, that's the logo. It's right there, I mean, the team got the logo from the steel industry.
I honestly didn't even notice that it just said steel. I thought you were just a steel staff.
That's where it comes from. Like if you go to steel.org, that's where it comes from.
You aren't a Steelers fan?
I didn't say that. I mean, some of it, I did go to WVU for a while. It kind of rubbed off a little bit, WVU is like satellite Pittsburgh, It is. All right. Okay. Attendance is up to date. I think I'm still sifting through a couple emails. I got slammed with emails this week about weather and whatnot, and people not being able to get to class. I have been slowly digging myself out of the email hole, so if I miss something, I will get to it, I promise. Homeworks 1.1 to 2.2 are graded. 2.3 is currently being graded. 2.4 was due today. 2.5 is going to be assigned today. So, what? Monday. Yeah. So it's going to be due Monday, and I'm going to give you a homework assignment on Monday, due Wednesday. So we're going to keep on trucking. Just because I'm not here Monday doesn't mean we can't do a virtual lecture here and there. And besides, I think the lecture will be pretty straightforward. I'll talk a little bit about it today. I might pull some of the slides up to kind of introduce some of the concepts. But basically what I want to do today is I want to do another tension member analysis example. I think it's just important to do another one. But this one is sufficiently different, not just from the last example that we did, but from a lot of other examples that we've done, so that I think that there's still a lot to learn from this. So this one's going to have some stagger. It's going to have some different stagger factors for the same net area path. There's a lot about this example I kind of like. So let's just recap. Factored loads, factored resistances. We are in LRFD land. So we compare our 1.2 dead and 1.6 lives against our factored resistances. Right now, we have two limit states associated with tension members. So here's our 1.2 dead, 1.6 live. These are the two limit states that we have associated with tension members. It is gross section yielding and net section fracture. What we are going to do a little bit later, and this will probably be like Friday of next week, is we're going to add one to this, and it's a limit state called block shear. Block shear is essentially for the lack of a better term, it's a little bit of a weird phenomenon around the connection region, where some of the connection region fails in shear, some of it fails in tension, and you kind of just rip a chunk out of the section of the member. And so the equation is actually pretty easy, but it's also pretty long. Like for gross section yielding, it's just these three terms. And yet if you look at the block shear equation, it's like this big. And the first time you see it, you're like, whoa, what's going on here? But it's actually not too bad. It's pretty straightforward. It's a lot of just gross and net areas. You just got to pay attention. But we'll get to that later. Tabs. If you haven't tabbed this would be a good one to tab, FY and FU for various ASTM specifications for various steel grades. We've got our complete expression for AN now. So we know that the net area equals the gross area minus the area lost due to the presence of bolt holes plus any necessary stagger factors. remember we add the stagger factors because the whole point of creating a staggered connection is to increase the net area. And so that stagger factor is an empirical term intended to account for the benefit that we get from a staggered bolt arrangement. Remember the effective hole diameter, we take the bolt diameter and we add 1/8 of an inch. You all are not going to like me when we get to bolted connection land, and when we look at the bolt bearing capacity of the members, we're not going to add 1/8 of an inch, we're going to add 1/16 of an inch because we're actually going to be looking at the physical dimensions of the hole. That is post-exam 1, so you don't need to worry about that now, but just know that's coming. That's for bolted connections. For welded connections, net area equals gross area. Shear lag factors. Shear lag factors are going to be in this table in the spec, table D3.1. If you haven't tabbed this, I would. This is probably between what I've already told you to tab and the shapes. This is probably all you need for the first exam. This is the example that we are going to do today. We're not going to look at a factored load. We're just going to compute the capacity. But I want to talk a little bit about this problem because it's kind of weird. We have this bolt arrangement here. So this is the cross-sectional view. And then I'm showing you this. And you're, what the heck's going on here? So let me explain. I decided to break out some Inventor. Okay, so have you ever used Inventor? Okay, all right. So I drew this member out in Inventor so that we could all kind of see it in 3D. So what we've got here is, hold on. So what we've got here is an angle, okay, and what I want to illustrate is the fact that we've got basically a staggered bolt arrangement. So one leg of the angle has 2 bolts in it, or 2 lines of bolts in it. The other has 1. But the thing that's probably the most important to pay attention to is that the stagger actually crosses the angle legs. So we have one staggered path that goes like this, and we have another staggered path that goes like this. So the stagger on this second path actually crosses from one leg of the angle to another. And so there's 2 points to recognize. Number one, we are going to have different stagger factors for this diagonal path than we are this one, okay? Because the dimensions are different. So instead of it being the gross area minus 3 bolt holes plus 2 stagger factors, it's going to be the gross area minus 3 bolt holes plus 2 separate stagger factors, and they're going to be different, like stagger factor 1 and stagger factor 2. The other thing is that I want you to pay attention to is, well, how are we going to do this? How are we actually going to determine what this distance is, okay? And the way that we're going to do that is this image right here. So what I am doing in this image is I am breaking out the samurai sword or the lightsaber if you happen to be a sci-fi fan, and I'm actually making a little cut right here, and I am taking this angle and sticking it on top. So I'm actually turning the angle sort of conceptually into an equivalent plate, okay? And I'm doing that so that I can determine this distance and that distance, and that's the one I'm sort of most interested in. Does that make sense? So I think what's most important is to just get the dimensions figured out across the board. Once you get the dimensions figured out, the rest is pretty straightforward. So let's blow this up a little bit. And I think what's probably most important is just making sure that we're all clear on the dimensions. Okay, so this angle is L5 by 5 by 1/2. So it's a 1/2 inch thick. What that means, when I say 5 inches, 5 inches goes from the back of the angle to the tip. Back of the angle to the tip, okay? So let's make sure that we're paying attention. What is that dimension right there? Say it again. 2 inches. What is this dimension right here? 2.5 inches? 1.5. Okay. So let's write it like this. Let's do 1.5 inches. With me so far? Now what we're going to do is we're going to indicate these dimensions over here. So what I mean by that is, would you agree with me that this dimension is the 1.5 inches? Like this dimension here and this dimension here are the same thing. What's this dimension? Okay. What about this dimension? So the only thing left to figure out is this dimension. Now before we do that, I want to ask, what is this dimension? Say it again. 10 inches. That's a good answer. That's wrong, but it's a good answer, and it's an easy answer to say, and I want to explain why it's wrong, and I want to do that kind of visually. Let's ignore all the bolts for a second, okay? And let's visualize what we're doing, okay? So here's the angle. What's this dimension? 5 inches, right? Okay. What is this dimension? In other words, I'm going. Well, no, hold on. Let's just keep it one step at a time. What is this dimension right here?
5 inches minus the width of the flange.
Well, and what is this? It's a 1/2 inch. The angle is 5 by 5 by 1/2, right? This is a 1/2 inch thick, right? So if this is 5 inches, this is 4.5. Does that make sense? Okay, so and that's 4.5 because this is a 1/2 inch, right? So what we are doing is we are samurai sorting right here, and we are taking this and sticking it on top. So what it's going to look like is we're going to have this plate right here, and we're going to have this separate plate with that, you know, where we cut it, right? And then we're going to take this and we're going to stick it on top of that. So at the end of the day, what it's going to look like, is this, and there's that little nub right there. So let me ask you this. What is this dimension right here? That's 5. But this, what is this? 4.5. See, I propose this is not 10. This is 9.5 inches. See, it's a kind of a trick question. So with the person that said 10, it wasn't that you didn't understand. This is kind of tricky. So does this make sense? Why it's 9.5? So the way that you determine this right here is you take that plus that minus that, because you have to take into account the fact that you overlap your thicknesses once if you do 5 and 5. Does that make sense? So now, can somebody tell me what this distance is? Say it again. 4.5. And how did you get that? Well, take 9.5 minus 3, 6.5 minus 2, 4.5. What do you think? Is that okay? Everybody okay with that? So that's what this dashed line is right here, is that sort of where you're severing it and then sticking it on top. Now, I don't want to move past this until this part makes sense, because this is probably the hardest part in the problem. Everything else is kind of routine. Yes, that's what I'm saying, yeah. That's exactly what I'm saying. Any questions? Okay. All right. So before we just start diving into this, does anybody know how many potential net area failure paths do you see for this problem? How many? Huh? Two. Okay, give me one of them.
Straight line.
Straight line. So this would be failure path 1. Failure path 2 is the one we probably can all see. Like that. So this one will tell us whether or not that stagger was even worth it, right? So we'll call this failure path 2, call this failure path 1. We'll just keep it simple instead of putting all those letters and saying, this is A, B, C, D, and this is A, B, C, D, E, or whatever. We'll just do 1 and 2. Sound good? All right. Now, we need some properties. Let's start off with the L 5 by 5 by half. Let's start off with the basics. Like, without the vagaries of the shear lag factors, what two properties can you tell me just right off the bat we are going to need for this angle? We're going to need the gross area, and the other one we don't really have to look up, but we are going to need. In order to determine net area, when we determine the area lost due to the presence of bolt holes, what do we need? You're doing it. The thickness, right? So we need the gross area, and we need the thickness. Now the thickness is a 1/2 inch. Now what is the gross area for an L 5 by 5 by 1/2? And we got that from table 1-7. Is everybody else able to find that? Okay, so we're going to need that. We are also going to need the material properties. Now for this problem, we are dealing with A36 steel. So we're going to need Fy, Fu. And I believe you've already had a homework problem where you had Fy and Fu. So Fy for A36 steel is what? And for Fu, what is it? 58. There's a range. Use the minimum. So this is 36 KSI, and this is 58 KSI. All right, and this is from table 2-4. Hold on. So I am trying to ensure that I'm writing references so that you're not going, where the heck is he coming up with these values? So, okay. So I'm going to do all my limit state calculations in the end. I could go ahead and do gross section yielding, but I'll just wait. We'll do that later. Let's do the net area. Okay. So for the net area, first off, we know that the bolt diameter is 3/4 of an inch. What does that tell us about the effective hole diameter? There you go. Again, 3/4, that's about the most common structural bolt that we use in the United States. Let's do failure path 1. So as we said, the net area is the gross area minus, and how many bolt holes are we going to subtract for net or path 1? 2. So 2 DET, which is, here, let me move this down a little bit so it doesn't crowd it so much. Or 4.79. So what is that? Do I have a second on that? Okay. Now let's do path 2. So path 2, we're going to do the gross area minus 3 bolt holes plus the stagger factors. Now let's talk about those stagger factors. What is the formula for a stagger factor? Let's put that up here. That's the formula for a stagger factor, right? S squared T over 4G. So is the thickness the same for both of these stagger paths? Yep. Is the S value the same for both of these stagger paths? Yes. S is along the load, along the path of the load, right? So S is going, so here's the tension member. We are yanking on the member this way. So stagger is measured this way. So the stagger path for, the stagger factor for this one and for this one, this distance is the same. What is the stagger? 1.5 inches. Is the G value different? Yeah, the G value is different. The S value is the same. If I asked that backwards previously, my apologies. But yeah, same S distance, different G distance. Apologies if that was backwards. So it's going to be, so we'll call it S squared T over 4G1 plus S squared T 4G2. So we need the two G distances. It doesn't matter what order we put them in. What are they? 4.5 and 1.5. And so what does this come out to be? .73 square inches. Do I have a second on that? What?
I done something wrong.
Take your time.
Yeah, 3.
Check your exponents and check to make sure you got a 4 on the bottom of your fractions. All right. So we've got two values here. Remind me, which one do we use? The smallest. Yes, sir.
Can you scroll up to the picture a little bit?
Yeah, hold on. Let me write this down so I don't forget. Yes, sir.
There's the 4.5 as the gauge.
For this one, yes.
Is that like since the curve in the angle is it basically just negligible because it's such a small curve?
That's a fair question. So yeah, you're talking about this sort of little fillet that you get from the process. So here's what I'm saying. For the purposes of the stagger factor, yes, it's negligible. But I'd also argue we are accounting for it. Okay. Here's why. What is 9.5 times 0.5? I'm asking you.
Was it 4 1/4?
4 3/4. You didn't bring your Casio FX115 ES Plus or similar scientific calculator, did you?
I thought I could do it in my head.
Oh. Okay, so I'm just messing. So 9.5 times a ½ inch is 4.75, right? Okay, so I'm proposing that if we were to just treat the angle as a plate, the gross area is 4.75. But what is the gross area? What are we using for gross area? We're using 4.79. So we are accounting for that little bit of additional area. Do you see what I'm saying? But that also sort of feeds into my point. It's not that much. It's a little bit, you know. It's just from the way that angles are formed, there's a little fillet there. So we don't really worry about it from a stagger factor perspective, but we do account for it. This is great stuff. That's a great question. Any other questions? This is good stuff. Okay. Okay, so there's the net area. Now, shear lag factors. So this is table D3.1. Now we're going to have a discussion on this one. So I want everybody to turn table D3.1. I want to look at this for a second. I'm going to ask a simple question. What's the shear lag factor for this problem? 1. Why?
Because both of the sides have holes. So it falls under case 1.
That's exactly right. I said that whenever you look at the shear lag factors, what you're looking at initially is case 1 versus case 2, right? Case 1 says all of the cross-sectional components are connected by fasteners or welds. Case 2 says some of them. It's never none of them, right? Can't be none because it's got to be connected to something, right? So it's either all or some. But in this case, it's all the cross-sectional components are connected by fasteners or welds. So in this case, U is U1 or 1.0. So what this basically means is that are there stress discontinuities? Are there weird stress patterns? Yeah, there are. But we're talking about capacities at the ultimate stage. We are loading this thing all the way to the ultimate tensile stress. And that at that level, because all of the cross-sectional components are connected, are there stress discontinuities? Yes. Are they enough that we really need to account for them? No. Does that make sense? So our U value in this case is 1. So now we can look at our limit states. So gross section yielding. So that's 0.9 FYAG. FY is 36 KSI. This is 4.79. So when I chug this out, what do I get? We'll say to like 1 decimal place, because when you're looking at like capacities in terms of kips, like 1 decimal place, that's enough. 155.2. Well, do I have a second on that? Okay, kips. All right, now how about net section fracture? So 0.75 FU ANU. So what's that? $162.3. Do I have a second on that? So what is the capacity? Does anybody kind of know? So gross section yielding governed. Does anybody kind of know what that means? Well, let me ask you this. Does anybody kind of feel like we did all those calculations for nothing? Because we did the net area calculations and folded it into a plate and did all this crazy stuff, and in the end it ended up not even mattering, right? Because the gross section yielding governed. If you feel that way, I want you to think about it another way. Remember how I told you that we employ stagger to increase the capacity? That's kind of what happened, isn't it? Right? We now are dictated by gross section yielding. If we had had the gross area minus 3 bolt holes and didn't have stagger, this would probably be less, and this would govern our design. So a little bit of extra math to show that it didn't govern. I mean, that's stuff you can spreadsheet these days. In the end, that'll save your client money. So don't shy away from the math if it's going to save your client money. Any questions? Anybody have any questions? All right, I want to talk a little bit about design before we call it for today, because we've got a little bit of time, and so I'm actually going to skip ahead a little bit to the next lecture, because I think this is important. So I don't have this posted yet, so don't, this is my lecture from last year, so the slides are old and whatnot. No, it's just the date's off. I want to talk a little bit about design because I want to illustrate this concept to you. Because my point is, what I'm going to put on that pre-recorded video is just like the plug and chug component of it. What I want to talk about today is the concept. So first off, let's take a step back. So today and the previous lecture, what we did is tension member analysis or tension member assessment, whatever you want to call it. But what that means is that we have been given a tension member and we're saying, okay, here's the tension member, how much can it hold up? Basically, right? We are assessing a tension member that has been given to us. But that is not design. Design is, I know I have a structure that's going to need a tension member right here. Which tension member do I select to safely resist that load? That's design. Design is selecting the components and the assemblages of a given system. That's what design is. So we need to talk about that for a little bit. I want to explain how we do it. Okay? So we covered tension member analysis. Given details about a member, we can assess the member's performance. Now we're going to talk about design. And what design means is that given some loads, given some constraints, we will select that element. Now I want to establish some ground rules in this class. We are going to adopt these ground rules for design in CE 414. I want to make sure we're all on the same page. We're going to be doing this for the entirety of the semester. Number one, we will always strive to select the lightest element. So what that means is if you had a choice between a W12 by, 45 and a W12 by 38, what have you, you pick the W12 by 38. Why the second one? Remember, when I say W10 by 49, what do I mean? The 10 is how deep it is. The 49 is the weight per foot, right? So the one with the smallest number on the end is the lighter one. Why am I talking about striving to select the lightest member possible? Why does that matter? Cost, right? It's going to save some money. Now, I want to be crystal clear. That is not always the cheapest solution. Take this building. How many different beams do you think are in this building? Hundreds, right? It might make sense on a project like this, instead of having 800 individually designed beams, to just pick a single section and use it everywhere, right? That might make it easier from a supply chain standpoint. That might make it easier from a fabrication standpoint, etc. But so I want you to keep in mind big picture stuff, that for homework problems and exams, our metric is going to be the lightest member. But I don't want you to think that is always the case forever. Simplicity tends to mean savings and economy more often than not. It's not always the case, but I just want to make sure that we're all on the same page. That's point one. Point two, we are going to establish constraints and guidelines on our homework problems and exams such that we all arrive at the same answer, okay? So for example, a common tension member problem for design might be, I want you to select the lightest W12 that will meet this given constraint. So we're all only selecting from W12s. How many shapes are in the manual? Look at this. There's hundreds of these things, right? You know, if I just said pick a tension member, I'd get 27 different answers and they might all be right. You know? So we're going to put some constraints, and admittedly some of those constraints might be stretching it a bit. But I'm trying to balance real world versus, us arriving at the same answer. To be fair, some of those constraints are real world. For example, I might be looking at this column behind right here, and I might be saying we are only going to select W12 columns or smaller, because the architect said that's all the room you've got to put in there, okay? So it's not that unheard of to have depth restrictions or anything like that. That's not that uncommon, okay? So I don't want you to think that that's unrealistic, okay? That is very realistic. So far, so good? Okay. So let's talk about some design expressions. So I want to look right here at this equation, okay? So what's going on here? Let's just myopically look at this. Here, I'll put a big circle around it, so this is all we're looking at. So we're in design mode. What that means is we've got a member. We're going to design a member or select a member to resist some given loads. So I know the loads. I got the 1.2 dead and 1.6 live. Okay. So what's the resistance? Well, it's 0.9 FYAG if we're just looking at this limit state. Okay. So 0.9, I know that. Fy. Now, let's say I didn't tell you what the yield stress is. Well, you could easily figure that out if you say, I know I'm going to use a W section, I can use Fy as 50 KSI because that's the preferred material specification. If it's an angle, we'll use grade 36. So if I look at that equation, what's the unknown? The unknown is the gross area, right? So I can divide both sides by 0.9 Fy, and I can say that my gross area has to be greater than or equal to Pu over 0.9 Fy, right? So given a factored load, what I can do is I can take that factored load, I can divide it by 0.9 Fy, and that gives me a gross area. And I know that if I pick a member that has a gross area of at least that, then I'm good, right? Boom, there's a design expression. I'm calling it gross area design 1 because there's two limit states. We have net gross section yielding, net section fracture. What about slenderness limits? I know slenderness needs, the L over R needs to be less than or equal to 300, so I can solve for a required radius of gyration, right? The design radius of gyration has to be greater than or equal to L over 300. So what I can do is I can say, all right, for a given design problem, solve for the required gross area, solve for the required R, and then pick a member that has at least those properties, right? That's a simple way of doing this, right? With me so far? Now, this is easy if all we had were these two limits. The problem is we don't. What about net section fracture? That one's kind of tough. Let's think about net section fracture for a second, okay? How do you compute the capacity according to net section fracture? Well, number one, you need to compute net area. How do you compute net area if you don't have a thickness? I'm asking. Yeah, I don't know. What else do you need for net section fracture? You need a shear lag factor. How do you determine a shear lag factor if you don't have the connection geometry? You don't know what the member looks like. How do you determine 1 minus x bar over L or any of that stuff? You have no idea. See, the problem is there is no closed form equation that we can come up with. We can't solve for a required gross area for this because there's too many unknowns. The net area is a function of the thickness, but we don't know what the thickness is before the member is selected. The net area, the shear lag factor is a function of the member geometry, but we don't know that in the beginning. So what I like to do is make a guess. A good common guess is that the effective net area, the net area times U, is about 75% of the gross area. That is a complete guess. It is an assumption. It is not always the case. Test the problem that we just did. Take the AN times U and divide it by the gross area and see if it was 75%. It probably wasn't. It might have been pretty close, but by and large, for every tension member that you could ever conceivably do, if you were to plot all that, that's about what it would be, about 75%. So I propose that what we can do is we can come up with a second formula for the gross area design, and instead of saying PU over 0.9 FY, we'll say PU over 0.75 squared FU. Now, why is it 0.75 squared? Well, it's 0.75 squared because one of the 0.75s comes from the resistance factor, and the other 0.75 comes from this being 75% of the gross area. And for simplicity, what I like to do is combine both of these into just a single expression. So, in other words, I'm going to calculate this, and take the bigger of these two. But the bigger of these two is basically this, whichever one has the smaller denominator. All right, does that make sense? Everybody okay with that? I want to stop for a second, see if anybody has any questions. Don't worry, I'm going to post these slides, so there's not going to be anything that you're missing too much. We're not doing any examples for any of this today. All right. So let me show you a step-by-step process and then make a couple comments and we're going to call it. So a step-by-step process for design is we're going to determine our factored load. We're going to compute our gross area for design and our radius of gyration for design. And then we're going to pick a member that the lightest shape that we can find that at least has a gross area bigger than this and a radius of gyration bigger than this. And then what we are going to do is analyze that member, just like we did in the last homework and in this homework. And we have to analyze it because in order to use this equation, we are making some assumptions. We must analyze it to verify those assumptions. Look at the member at the end of the day. If it's strong enough, great. If not, pick another member and try again. And we'll go through some examples on this here in a bit. But before I call it, let me give you my final little rule of thumb. Does anybody know what this image is from? Who said the Wheel of Fortune? It's The Price is Right. That's where The Price is Right. This is from the Wheel. Can anybody tell me how this works? Anybody remember how this works? Say that again. You spin it. No. But what happens if you get over 100? You're out, right? So the idea behind spinning the wheel is you want the number to be as close to 100 as possible without going over, right? Okay, if you spun the wheel and you hit 95, would you spin again? No, right? Okay, everybody knows what I'm talking about? Okay, so step 4 is a very, very critical part in the process. What you're going to do is you have a trial shape. You are going to analyze it to verify its capacity. But if you get a member that's good, the question is it too good? Like, for example, if you pick a member for a 200 kip load and its capacity is like 700 kips, it's probably way over designed. You can probably back it down a little bit. So how do you know whether or not your member is efficient or not? So what we do is we compute an efficiency. We take the final load over the final resistance. And so it's like a percentage, right? And so in bridges, we call that a performance ratio. Here, we're calling it an efficiency. It's kind of the same thing. The idea is that if that number is 90% or greater, you're good, okay? So what I'm getting at is if you have a really, really low efficiency, I would check the next lightest member. But if it's like 90% or greater, it is very possible that the next member is good, but I'm not going to make you check it. Does that make sense? Because here's the thing. You're never going to, like, it is very rare to get a design with 100% efficiency. Just because of the messiness of the numbers. Like, you're not going to get, it's not going to be perfect. So as long as your design is good enough, like if you have a member that has 99% efficiency and you're like, oh, I can do better. So I'll select the next lightest one. The next lightest one will probably fail. So there's no point in doing all the math, is what I'm saying. So if you get close, if you get to 90%, you're good. Most of the problems, at least like on an exam, I formulated. I'm not trying to make this part confusing. Questions? All right, so we're going to do a tension member example on the video next time. As long as you understood this stuff and what we've been doing so far, this will pretty much be pretty straightforward. All right, any questions? I will see you on Wednesday.
I'll see you on Monday. Online.
Well, okay, yeah, that's true. I'll see you on Wednesday. You'll see me on Monday.
I'm being